Hello everyone, this is Abdullah Khalifati. Today I'm going to be presenting our benchmark TSM Bench, benchmarking time series database systems for monitoring applications. This work is a joint collaboration between myself, Morad Khayati, and Philippe Guillemot from University of Fribourg, Anton Dignos from University of Bolzano, and Jalal Difallah from NYU Abu Dhabi. This work was originally motivated by the challenges that we face when we start working with hydrometric station data in Swiss water sources such as rivers and lakes. Such stations contain a variety of sensors that measure different phenomena about water measurements and that result in multivariate high-frequency time series data with different features. Each station then collects the data from different sensors and sends it to a time series database systems where data is ingested and made available for analytical queries. After consultations with hydrologists and data analysts, we identified a set of requirements that are necessary to help practitioners understand and analyze time series data for monitoring tasks. Such requirements include data exploration, usually using data fetching, anomaly detection, forecasting by building predictive models to predict the future behavior of the data, reducing the frequency of the data using downsampling to better analyze the trends, and doing the opposite using upsampling in order to impute the missing values, and finally, to compute the similarity between different sensors and stations. Relational database systems are not well equipped to handle large volumes of time series data. This is because they lack the optimized support for handling large volumes of timestamp data with frequent inserts and complex temporal queries. This has given rise to specialized systems, time series database systems that are meant to store large volumes of time series data as well as to process and query the data in real time. Choosing the best system for a given use case remains, however, a difficult task due to the diversity and the sophistications of these systems. Benchmarking time series database systems can provide a systematic way to understand their abilities, their limitations, and their trade-offs. A couple of benchmarks have been introduced to perform the evaluation of these systems. These benchmarks mostly implement static queries on a subset of relevant systems. This means that these benchmarks evaluate the type of the queries, but not the impact of the dimensions and the configuration of the queries on the system's performance. These benchmarks also assume that the generation and the querying happen asynchronously. This means that they happen not in the same time. Finally, they use simplistic data generation or simply random data. This can have a tremendous impact on systems performance. Our benchmark, TSM Bench, evaluates 7 popular time series database systems by providing dynamic query evaluation for both offline and online queries. This means that we evaluate the querying and the ingestion synchronously and asynchronously. We also introduce a time series generation method that produces realistic time series data in large volumes efficiently. Finally, we provide recommendations that help understand and navigate systems performance to better choose the most suitable system for a given use case. The pipeline for our benchmark starts with the stations that contain different types of sensors, and each station collects the data from the sensors and sends them to the time series database systems. For our benchmark, it's mostly composed of 3 main components: the data generator that generates large volumes of realistic data and feeds them to the systems to make them ready for the next workloads. The second component is the workload executor that generates a variety of workloads and executes them to the system. And the third component is the statistics collection module that collects the different metrics from the systems to represent their performance. Our data model looks like this. The data is mostly ordered by time, and we also have the additional partitioning dimension, which is the station ID, where each station ID has its respective sensors. In our benchmark, we introduced TS-LSH, a new time series generation method that produces realistic time series data in large volumes efficiently. Our method is based on generative adversarial networks and takes as input time series data partitioned into segments and uses the adversarial game between the generator and the discriminator, where the generator aims to generate synthetic segments like that look to the original time series, where the discriminator aims to distinguish between the synthetic and the original time series data. Once the training is done, we use the generator to generate a large volume of synthetic segments. In order to generate longer time series data, one option would be to increase the dimensions of the generative adversarial networks. This is, however, prohibitive in time due to the complexity over the computation overhead resulted by the neural networks. What we suggest instead is to use the original data as a reference and to concatenate the synthetic segments. This is indeed what we do using the locality sensitive hashings, or LSH, where we use the GAN to generate large volumes or large number of synthetic segments, and then we hash them, or we store them into locality sensitive hashing tables where similar segments are stored in the same buckets. And then we do a lookup where we query the original segments into the synthetic segments in order to identify candidates that are fit to represent the original segments in the synthetic data. This helps us produce large volumes of time series data that are both larger in length and in number. We also prove that this generative process is efficient. Matter of fact, it is sublinear to the size of the original data and is linear to the size of the generated data. Moving on to the evaluation part of our benchmark. Our workloads were designed in a way that they cover and evaluate the performance dimensions of the data accessed, processed, and output by the queries, as well as the number of operations that are operated and that are performed by the queries. The impact of the executing the querying and the ingestion simultaneously, and also the impact of the data features on systems storage and compression performance. For the experimental setup, we evaluated 7 popular time series database systems, namely ClickHouse, Druid, ExtremeDB, InfluxDB, MongoDB, QuestDB, and TimescaleDB. We used TSLSH, our generation method, to produce 2 datasets, one with long time series data and one with a large number of time series data containing around 500 million and over 17 billion data points, respectively. Our offline workloads evaluated 7 queries, including fetching with filtering, aggregation, downsampling, cross-sensor average, and correlations between multiple sensors. Our online workloads involved executing these queries under concurrent ingestion when we vary the size of the ingested data and also the rate of the ingested data, and we study the impact of that on the query performance. And finally, we evaluated the compression workload. Moving on to the results of our benchmark, we report here an example of our query results, which is the aggregation and downsampling. In this query, we perform a series of aggregations for given sensors and for a list of stations within a time range. We vary the number of stations, the number of sensors, and the time range where the query is executed. The results show that ExtremeDB and TimescaleDB are the fastest in the case of simple aggregation. This is particularly visible for selective time series under 1 day. Both these systems use an array-like format. First, ExtremeDB using its vertical sequence format that stores the time series data in a single sequence, and TimescaleDB thanks to its historical compression method that also stores time series into a single array. This makes these systems particularly efficient for aggregation queries because the data can be read with a simple read. Also, we see that ExtremeDB and ClickHouse are well suited for downsampling data as well as for high selectivity aggregation queries. ExtremeDB, here again, is able to perform efficiently for the downsampling query because it only manipulates the timestamps and is able to perform a series of aggregations efficiently thanks to its sequence-like format with very few reads. And ClickHouse is able to produce efficiently for highly selective queries thanks to its parallelization capabilities, as well as to its sparse indexing method that output a series of rows in a bulk instead of returning rows individually. This makes it particularly efficient for queries with a high selectivity. For the online queries, we insert data to the systems concurrently with the queries. We vary the size of the data that is inserted by second, or the insertion rate, and we report the runtime results in milliseconds. The lower the results, the better. First, we see that the queries do not block writes for all systems. This is because the overhead caused by the queries is significantly lower than that caused by the writes. We also see that QuestDB and ClickHouse are the best for low insertion rates, whereas InfluxDB and MongoDB provide the best runtimes for very high insertion rates. This is because InfluxDB and MongoDB simply append the data during insertion to their storage without any more required merging or sorting. This makes them particularly efficient for online queries where the data is being inserted in the time series database system in high rates. For our compression workloads, we use TS-LSH to generate datasets by varying their features and by studying their impact of the features on the storage size of the database systems. Here we report the results for varying the percentage of repeats and the percentage of missing values. The results show that all systems benefit from the existence of repeats. Particularly, ClickHouse and Druid perform the best. ClickHouse supports the run length encoding compression algorithm that only stores the difference between the consecutive values in the data. This makes it particularly efficient for data with high repeats because it does not have to store the delta for these values. For the Druid system, it supports the bitmap compression algorithm that only uses one bit to represent the presence or the absence of a given value. This means that for datasets with a high repeat percentage, it is able to take advantage of that to significantly reduce its storage size. For the data sparsity feature, we can see that only ClickHouse and Druid can take advantage of this feature. Moving on to the recommendation part of our presentation, we have summarized our results by assigning a score for each system across 7 discriminative dimensions that help us compare the time series database systems for our benchmark. We assigned a score between 0 and 5, where 5 is the highest. And while we find that there is no silver bullet point, we have seen that some systems excel in certain dimensions, where other systems provide better trade-offs. For example, ClickHouse provides the best for large queries with large output and for large datasets, as well as for loading performance. On the other hand, ExtremeDB performs the best for selective queries such as aggregation, window operations, and filtering. We see that InfluxDB excels for the online queries and their high rates. We also found that TimescaleDB provides competitive results across all dimensions. And wanting to go beyond the actual systems and to understand their underlying architectures and to find a recommendation of the best architecture, we have found that there is no single architecture that outperforms all the systems for all the workloads. However, we have identified a set of factors that significantly impact systems' performance for both offline and online queries. For the offline workloads, we have seen that the query selectivity and the dataset size impact the most systems' performance. For example, for queries with a low selectivity, sequence-like formats like ExtremeDB are highly recommended. When the dataset size increases, then using partitioning provides the best results. For the offline workloads, we have also found that the query selectivity has a tremendous impact on systems performance, but we also found that the insertion rate has an important factor. For low insertion rates, for example, and for selective queries, B-tree-like format like ClickHouse perform the best results, but when the insertion rates increases, then log-structured merge tree formats like InfluxDB perform the best results. To conclude our presentation, we introduced TSM Bench, a comprehensive benchmark that evaluates offline queries, online queries, as well as compression workloads. We also introduced the new time series generation method that produces realistic time series data in large volumes efficiently. We also provide a recommendation for the decision makers based on the actual database systems, on their underlying architectures, and on the different workloads and the queries that could be executed. Our code is shared and open in GitHub, and future work includes mixed queries workloads and multi-tenancy scenarios. Thank you for your attention.